In this video, we look at determining the future value of a single amount, and we'll see how that amount is determined using a financial calculator and also by using Excel's built-in future value or FV function. To begin, we need an example, so let's consider the following question. How much would $1,000 invested today in an account that pays 5% quarterly compound interest be worth in 10 years? This is a very practical scenario. We have $1,000 that we'd like to save and put on deposit and let it earn interest and have that interest compound as such that the interest that we earn in a given period adds to our investment base, thereby increasing the amount upon which we earn interest in the next period. Then we'd like to know how much we could withdraw at some point in the future. And so let's begin by defining a few variables. First of all, we've got the amount that we will deposit today. We refer to that as the present value. In terms of a variable, let's use the variable V sub 0 to represent that. That's the value of our investment today or at time 0. And then we have the interest rate. This is an annual interest rate, as interest rates are always specified per annum, that is an amount per year. Let's use the variable R to represent that. Then we have the compound frequency, and that's how many times per year we will add interest to our investment base, and again, that thereby increasing the amount upon which we earn interest the next period. As specified here, we will be compounding quarterly. We'll use the variable N to represent the compound frequency. That is, we are compounding 4 times per year. Next, we have the investment horizon, or the term, in years. Let's use the variable T to represent that. Now we'll see that in the context of our computations, the investment horizon needs to be specified in terms of the number of compound periods. And so that will always be T times N. So in the context of this problem, that would be 10 years times 4 quarters per year, which would give us 40 quarters in the investment horizon. So we'll consider that as we specify our final variable, which is the future value. It's going to be the value at T times N periods in the future. And again, that will be referred to as the future value of our investment. So let's consider the following formulation of our problem. As we just specified, the value today, our present value, is equal to $1,000. If we step ahead just 1 quarter, that is the value at time 1, the end of time 1, the value at that point should be the value that we began with, our present value, plus the interest that we earned for that first quarter. And the interest that we earned for that first quarter is, of course, based upon the initial amount invested multiplied by the quarterly interest rate. The quarterly interest rate is our annual rate, R, which in this case is 5%, divided by the compound periods per year, N, which again is 4. So this would work out to 1.25%, or as a decimal, it would be 0.10125. Now if we notice that in our expression we've got a common term in both of our, or a common factor in both of our terms, we've got the present value. That means that we can factor that value and get a new expression. So the value at time 1, or the end of the first quarter, is equal to the present value multiplied by 1 plus our quarterly interest rate. And in the context of this problem, it would be $1,000 times 1.0125. So our investment would have grown to about $112, or rather $1,012.50. If we move to the end of the second quarter, the value of our investment should be the value at the end of the first quarter plus the interest that we've earned on that value in the second quarter. And once again, we'll notice here that there is a common factor in the terms here that can be factored. And we'll do that. And so what we'll have is the value at the end of the first period multiplied by 1 plus our quarterly interest rate. Of course, we see that that repeats, which means that we can express that as a single amount raised to a power, raised to the second power. So the value at the end of the second quarter is equal to the present value multiplied by 1 plus our quarterly interest rate squared. And in the context of our problem, that's 1,000 times 1.0125 squared. Now what we'll notice here is that we have a pattern that develops such that if we were to consider back at the end of period 1, the value there was the present value multiplied by 1 plus the quarterly interest rate. There's implicitly a 1 here, okay, as an exponent. Okay, there's a 1 there, so that 1 agrees with the subscript for that period. And then there at the end of period 2, we have the expression where we've got a exponent of 2 that agrees with our subscript. And therefore, we get a generalization of this that is expressed here. Okay, that the future value at the end of t times n periods, compound periods, is equal to the present value multiplied by 1 plus the interest rate for the compound period raised to the number of compound periods, t times n. So in the context of our problem, we had the value at the end of 40 quarters, that's 10 years times 4 quarters, is equal to $1,000, the present value, multiplied by 1 plus our quarterly interest rate, raised to the number of quarters in the investment horizon. And that's just rewritten here, 1.0125 raised to the 40th power. And that amount, 1.0125 to the 40th power, computes to 1.64362. We refer to this as a future value of single sum factor. In this problem, since we're multiplying by 1,000, getting the final result is easy. We just move our decimal place 3 places to the right, and we get our result, $1,643.62. So at this point, let's consider calculating that amount with a financial calculator, and then we'll move to using Excel's future value, that is FV function. Okay, looking at our financial calculator now, there's really 2 different ways we can go about solving this problem. One is to use a key that will allow us to raise a number to a power. And that's a key that appears on not just financial calculators, but scientific calculators and just typically your very basic calculator. And so you may have a calculator that's got, say, a y to the x key or an x to the y key, or it might be specified as x to the n, something along those lines, but it allows you to raise a number to a power. And for many time value of money problems, that's really all you need. So we'll see here in our problem that if we consider our formulation that we had where we want 1 plus the quarterly interest rate, that was 1.0125, we needed to raise that to the 40th power. So I enter that number into the calculator. I then enter the exponent to which I want to raise that number, and activate the y to the x key. And that gives me the factor that we saw in our previous example, 1.64362. We can then merely multiply that by 1,000 and get our final result, $1,643.62. Okay, let's clear that. Now let's look at using some built-in functions that this financial calculator has. And we'll notice across the top here, the top row, that we've got a couple of keys that are designated PV for present value and FV for future value. We also have a key for N, which is really the number of compound periods in the investment horizon. And then we've got I, which is the percentage interest rate per compound period. So to solve our future value problem using these keys, we have to take, we might say, a cash flow perspective. That is, we're going to take $1,000 today and essentially buy an investment. So that's a cash outflow. That means that as we enter the present value of our investment, we enter that as a negative amount. So I use my change of sign key, which is up here, to designate that. And again, the idea is we're paying $1,000 for an investment today, and so I will enter that in the present value register. Now we need the number of quarters in the investment horizon. As already noted, that was T times N, or 10 years times 4 quarters per year, which gave us 40. We enter that in the N register, and then we've got the interest rate per quarter, and we do specify this as a percentage rather than as a decimal. So we enter 1.25. Recall we had 5% interest divided by 4 quarters. That gave us 1.25% per interest per period per quarter. So we enter that in the I register. Now all we have to do is activate our FV, or future value key. And that gives us very quickly our result, $1,643.62. So let's move on now to look at how to solve this problem using a built-in function in Excel. So we have an Excel spreadsheet set up here, and already got a few descriptors in here, the variables that we were using in our computations before, and descriptions of those variables. So we've got V sub 0, which is our present value, again the value at time 0. We've got T, which is the investment term in years, N, which is the number of compound periods per year, R, which is the interest rate per annum, and then there's our future value, which is the variable V sub Tn, Tn again being the number of compound periods in the investment horizon, the term in years multiplied by the compound periods per year. From our example problem, I've already got the inputs here. $1,000 invested today for a period of 10 years when we're compounding 5% interest on a quarterly basis. And now we merely want to determine the future value. I'm going to go up here and activate the insert function icon. And of course there are several sections of built-in functions in Excel. The one we want is the financial section. We'll scan to where we find the FV function, and there's a little description here that's provided for that. It says it returns the future value of an investment based on periodic constant payments and a constant interest rate. So this function has a degree of flexibility in that it can be used to solve for not just future value of single sum type problems, but also future value of annuity problems where you have a stream of constant payments or constant deposits that you're trying to evaluate. So let's go ahead and activate the OK button. It will bring up a pop-up window here for us where we input the parameter values.
And so the rate will be the rate per compound period. And so that will be, again, our quarterly interest rate, which is our annual interest rate divided by the number of compound periods per year. Essentially, I've put that rate in as a formula. And then regarding the parameter N per, the number of compound periods in the investment horizon, that would be the investment term in years multiplied by the number of compound periods per year. So notice that both of these calculations return the values that we expected, the quarterly interest rate being 1.25% per quarter, and then we had 40 quarters, 10 years times 4 quarters. Since we're not doing an annuity, let's leave the payment field blank. But the present value, we do have that as $1,000. Now, one thing we'll remember here, like we saw when using the financial calculator, we have to take a cash flow perspective in that we're going to take $1,000 today and essentially buy an investment. So that's a cash outflow, a negative cash flow. That means that we enter the present value as a negative amount. So I put the negative sign in and reference cell C1, which is the present value. And notice that the function has already generated the return that I expected here, the value, $1,643.62. So I will hit OK, and that gives me my result in the cell. And so the nice thing about Excel is that you can then do some what-if analysis by merely changing your parameter values. You can see, for example, if we wanted to see how much our investment would grow to if we were to deposit the money at 6% interest, we put in 0.06 and see that it grows by a considerable amount to $1,814.02. Or if we wanted to say, well, what if we wanted to only leave it on deposit for 5 years? So we'd see that our investment is $1,282.04. Also, you could say, well, what if the compound frequency is increased? For example, if we're compounding every month, we put in 12. And we see that our investment grows by a little amount, $1,647.01. And in the extreme, you might say, what if we're compounding at a very high number of times per year? You put in 100,000. May sound a little ridiculous, but there is the concept of continuous compounding and continuous discounting that applies to the pricing of certain types of investments, in particular derivative securities, for example, interest rate futures contracts and interest rate swap agreements and so forth. Those have the concept of continuous compounding, continuous discounting involved in their pricing, and so it is actually a practical thing that we'll consider in a later video. But we'll see that our investment grows by a fairly small amount as we go to an extreme number of compound periods per year. So again, there's more to come. We'll look at future value under continuous compounding in another video. We will also look at present value concepts in another video. And then we'll also probably in a couple of videos look at future value of annuities and also present value of annuities. If you have questions or comments about this video, you may email me at drgtoddjackson@gmail.com. Thank you for joining me.